Okay, so we're back here continuing to talk about pipes and pipelines. And so the book has a little bit of discussion about pipes in series and in parallel, so I thought we would talk about that a little bit also. This is very important when you want to get into looking at water distribution systems. And I don't think we're going to have time to really go into that in a lot of detail, but um, anyway, this is an important topic, and so we'll try to introduce it a little bit here. So the basic concepts of pipe flow that we've talked about for one pipe can be extended if we have pipe systems where you have a lot of pipes that are connected together. So we still can use energy balances, we can still use mass balances, we can still use friction losses. All those things work, but there's a few other things we have to know. So what are those couple other things? And so the ideas really are similar to those that you would use with electronic circuits. So I don't know if you guys take circuits anymore, but I took a circuits class, and we learned about how you analyze a circuit where you have a network of different wires and resistors and so on. And so the main idea there is to remember that pipes in series have the same what? So basically, if I have water or something else flowing from one pipe into another, if they're connected in series, what could I say about those two? I need math, I need equations to use to solve these problems. I can do a mass balance, and I would say the flow out of this one is equal to the flow into that one. So the pipes in series have the same flow rate. Okay, and maybe not too hard to come up with that one. Pipes in parallel, on the other hand, so if I have two different paths, two different pipes that connect, they branch, and then they connect back together, what could I say about those two? And it's not flow rate if you were thinking that it's that. And so you might just keep in mind that water is going to follow the path of least resistance, right? So path of least resistance. So if it has two different paths that it can take, which one is it going to take? It's going to take the one with least resistance. So if there is water flowing through both paths, what does that tell you? It tells you the resistance is the same. So they have the same resistance, or we might say the same head loss. So we have the head here and we have the head here in our two choices, and then the loss, the difference in head between the two, is going to be the same whether you go this way or that way. So we can take these two ideas and then everything else we've learned and use it to analyze pipes in series and parallel. So let's look at a series example here. So here we've got a reservoir, and it is above some outlet. It's discharging here 100 meters below that. So we've got 100 meters of head basically pushing through there, and then it's also got to push through this long series of pipes, 3 kilometers long. So 100 meters ahead to push it 3,000 meters through a pipe, going to be a bunch of friction losses. So we've got a valve out here at the 2,000 meter mark, and then there's a confuser here with a 40-degree angle to reduce from the 25 to a 20 centimeter diameter pipe. So I don't know if you would see a situation like this in a real problem. I don't know, maybe you would, but bigger pipe is going to give you less friction losses, but it's going to cost more. So it's a tough decision you always have to make when you're looking at a pipe as an engineer. But maybe in this situation they said, well, we want some friction losses to go away here, and it's worth the extra pipe, but not here. I don't know. So, but in any case, we've got two different sizes, so we've got pipes in series. And so how are we going to analyze this? So it might be helpful for us to start by saying, what do we know and what do we not know? So I made a little table here of unknown, and I have another one of knowns over here. So stuff that we know that might be useful. Here we're given stuff in metric units, so we're going to have G in metric units. New, it's just regular water at 20 degrees, so if we go look that up, 10 to the minus 6 meters squared per second. Roughness height for, let's see, smooth concrete in this situation, so we'd go to our table and look at this low value for the roughness height for concrete. Yeah, and yeah, that's the same for both. So we could actually have a different roughness in each pipe. There's no reason we couldn't. In this example, they happen to be the same. Really doesn't matter though. They don't have to be. So 0.18 millimeters or 0.00018 meters. So I kind of like to do the unit conversions early so that we don't have to get tripped up with them later. And E1 is equal to E2, so they're the same. D1, we're told the diameter in the first one is 0.25 meters, and the second one it's 0.2 meters. Again, I'm doing the unit conversions now. The length of the first one is 1,000 meters. Okay, 1,000 meters here, and then the second one is 2,000. All right, and then we're going to have some entrance loss coefficient. It says it's sharp. If we go look that up, K entrance is 0.5. And then we've got a valve. We have a KV of 5. And then we've got K for the confuser. So for this one, we would have to go look at our table here. And K confuser, it's actually written in terms of the velocity in the smaller pipe, if you look at this. So and then the confuser loss depends on the ratio of the two areas. So here we've got, let's see, I think I just wrote the number down, but so A2 over A1 is going to be D2 over D1 squared, because they're pi d squared over 4 for both of them. So the pi's and whatnot cancel. And so D2 over D1 is 2 over 2.5 squared, and that's like 0.64, I guess, right? So this is 80%, 4/5 squared. I'm doing all that in my head. Seriously, you can if you know how to do some fractions. 2 over 25 is 20 over 25. Divide by 5 on the top and bottom, you get 4 over 5, which is 0.8 squared, 0.64. All right, so that means it's between these two and then 40 degrees, so it's kind of like right in there, and so yeah, we get that K is 0.02. All right, a lot of work for a number that's really not very important, because 0.02 for a minor loss is pretty small, especially in a big long pipeline. But anyway, that's how you would use that table, for example. I'm not going to show you every single one of those. You have to be able to look numbers up in tables on your own. That's something I assume you can do. All right, so this is stuff that we know. What do we not know? Okay, so we've got diameters, we've got lengths, things like that. And so we know we're doing friction losses, so that's going to depend on D and L. And then if we want to get our friction factors, which, okay, we don't know those, so we don't know the friction factor, F1, and there's no reason that we have to have the same friction factor in both. And in fact, you're going to get something different because you have a different diameter, means you're going to get a different velocity and different Reynolds numbers. So yeah, you're not going to have the same friction factor. But I'm going to call them F1 and 2. So, and yeah, I don't know the Reynolds number. That could be different in each. So Reynolds 1 and Reynolds 2. There's a velocity in each that is not going to be the same. There's Q. We don't know. So I'm just going to call that Q without a 1, because we know that the Q is going to be the same in both pipes. That's the one thing we know. Here we go. This is what we know. Everything else we're doing is going to be the same kind of stuff that we do for one pipe. But when we have two, we give everything subscripts, and we just have to remember that Q will be the same. All right. So there's going to be some head loss across this pipe, and then there's going to be some head loss across this pipe. So that's really another thing that I don't know. I know the total here. I'm losing 100 meters of elevation. All right, but I don't know how much I'm losing on the first one and the second one. So delta H1 and delta H2. All right, so look at all these unknowns. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 unknowns means I need 9 equations. 9 unknowns. Oh my goodness, it can't be done. It can be done. It's actually, we can do it by hand here. This problem is definitely easier done in Excel. I don't think I'm going to spend time talking about how to do this one or the parallel in Excel, simply because I don't have a whole lot of time to go into this, and you're not going to have Excel in the FE. I'm mainly going over this because this could be on the FE. But this will also help you with your general problem solving for these things. So, all right, so 9 unknowns, we need 9 equations. So I'm not going to write them all down. But what do we have? We have Darcy-Weisbach equation for both of them. That's 2. We've got energy loss equation for both. We've got a Reynolds number formulas that you can write down for both in terms of the velocities. We have Q is equal to VA for both. So we've got lots of equations to work with here. And so really the way we're going to solve this one is going to be iterative, and the key unknown here, I would argue, is going to be the flow rate. And again, this is something that I just kind of know from experience, but if we knew the flow rate, if I knew the flow rate, could I figure out V1? Yes, not hard at all. Q equals VA. This would be easy if I knew Q. Could I figure out V2? Yes, also easy. Once I have V1 and V2, Reynolds numbers, also easy. dV over nu. These are easy. Once I have Reynolds, and now I know the roughness heights, right, I could then go and figure out F1 and F2. So again, if I know Q, that means I know the V's, I know the Reynolds, and then I know the friction factors. And then I can figure out the friction losses using an energy equation with Darcy-Weisbach. So basically, if I knew Q, I know everything else. So how am I going to do this then? Procedure to solve this. I'm going to pick Q. I'm going to guess. And then I can find V1 and V2, find Reynolds 1 and Reynolds 2. Okay, so this from just Q equals VA, this from dV over nu, and then look up the friction factors or calculate them. Then I can figure out the head loss. And then once I have done all that, then I can check closure. So I again have this situation where I'm guessing, I'm going to guess Q, and I'm going to be wrong the first time. Here I don't have any way to really know what Q is in advance. I can't make a good guess, so I'm certainly going to be wrong. So I need some way to deal with that. So I'm going to guess Q, I'm going to follow that logic through, and you have to follow it all the way through, and then we're going to check the closure. And so our closure condition is going to be based on an energy balance. Okay? And we're going to see if that's right, and then we adjust Q. And then we go back, okay, and repeat everything until we get the right one. And so if we do this correctly, we don't have to iterate a lot, but this is why it's easier to do this in Excel. But so I will do this one to show you how. Okay, so that's the procedure we're going to use. So let's do a quick energy balance. And we'll do that here. So energy balance, if I pick this point 1, and then I pick this point 2, here I'm going to know that P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2 plus my losses. Okay. Both of these are open to the atmosphere, so the pressure is atmospheric, means those are gone. V1, it's a big tank, it's gone. All right, so I've got Z1 minus Z2, which I know is delta Z is equal to 100 meters, and that has to equal to the head loss, which is going to be what? It's going to be sum of the K's times V squared over 2G plus, I've still got this V squared over 2G here, and so V2 is, so some of the K's, I guess, well, I shouldn't write that out yet. Let's just leave it as V squared over 2G plus HL. I'm out of room here, so I'm going to have to write it again anyway. Okay, V squared over 2G, V2 squared, that is, here at the end of the second pipe, plus whatever head losses. And so there are head losses in the first one and in the second one. So I'm going to write all that out here in the next page and work with that. Okay. So we have delta Z is equal to V2 squared over 2G plus, so we're going to have an entrance loss. If we look here, we're going to have an entrance loss that's going to go with V1, and then we're going to have our confuser loss goes with V2. Remember, our equation is written in terms of the second pipe. It doesn't depend on the velocity in the first one. So here we've got our entrance loss, we've got our friction losses in the first one, and then for the second pipe we've got our confuser, friction losses, valve loss, and then we've still got this energy head there at the end that we have to consider. So we've got V2 squared over 2G plus K entrance times V1 squared over 2G plus F1 L1 over D1 V1 squared over 2G plus F2 L2 over D2 V2 squared over 2G plus K for the confuser times V2 squared over 2G plus K for the valve times V2 squared over 2G. And I believe that is everything. And so we've got, so if you look here, we've got all these V squared terms, but so I'm going to group them together. Delta Z, which is 100 meters, is, so for the first one we've got KE plus F1 L1 over D1, all that times V1 squared over 2G. So that's those two terms, and then here plus a 1 for this one, plus F2 L2 over D2, and then a KC, and then a KV times V2 squared over 2G. So here we go. This is my closure condition. So what I need to do is guess a Q, figure out V1 and V2, figure out the Reynolds numbers and then the friction factors, and then I can plug all this in and I can see if my guess for Q, when I plug it all in here, gives me 100. Most likely it won't, but that's our condition. And so you can easily set this up in Excel where you pick a Q and you put in all the things you know and you set up this equation as your closure condition. But we'll do it by hand here. So let's see. All right. Yeah. And I'm going to call this whole thing delta H1 and this whole thing delta H2. So the head loss in the first one and the second one associated with each of the two velocity terms. Just so I can kind of break these calculations apart because this is a lot. Okay, so let's guess. We're going to guess Q, and I'm just going to randomly guess that it's 0.2 cubic meters per second. Again, I do not have a smart way to guess this. The smartest way I could tell you would probably be to assume it's between 1 and 2 meters, 1 or 2 meters per second for the velocity in one of the pipes, and then see what Q that gives you. But because it's typically going to be around that in a real pipe. But anyway, here we're just guessing it's 0.2, and then we're going to see what happens. So now we're going to get V1 is Q over pi over 4 D1 squared. So 0.2 over pi over 4 times 0.25 squared gives me 4.07. And then I'll write V2 over here on the right because we're going to need to do a lot of writing. So I'm going to use the whole page. 0.2 squared. Oh, this is supposed to be a 0.2 for Q. And that is 6.37. Okay. And now I can get the Reynolds D1 V1 over nu. And likewise, I can get the Reynolds for the second. And let's see, that is 0.2, 5 meters times 4.07 over 10 to the minus 6th, and so I get that it's 1 times 10 to the 6th. Second one, 0.2 times 6.37 over 10 to the minus 6th, and that gives me 1.3 times 10 to the 6th. To get my friction factors, I'm going to need my E over D. And so that is 0.00018 over D1 we said was 0.25, and so I get that that is 0.00072 E2 over D2. And remember, these actually won't have to calculate again once I've done them once. They don't have to be updated when I iterate. Alright, so 0.00018, and again, these E values don't have to be the same. They could be different kinds of pipes, but this wouldn't really change the procedure at all. Okay, in other words, I'm not making it easy and showing you, oh, it's so easy this way, and then it's really not any harder if they're different. Okay, and so that is 0.0009. Now I have the Reynolds. This is Reynolds 1 and Reynolds 2. So from these, I can then get my friction factors. So if I use the Moody chart, 10 to the minus 6th is right here. E1 over D1 was 0.0072. 0.0072. So kind of between these two lines. And so, it's right in there somewhere. Looks like that's a 0.0. Let's see, I put that it's 0.017. Well, so, yeah, let's see, 0.0072. Looks like it's closer to 0.018 to me, but I've written down 0.017, and so we'll just roll with it. It doesn't really matter. We're going to have to update it anyway. Okay, Moody. And then F2, likewise, if I look that up, is 0.019. And then for Moody. And again, hopefully you've seen enough of that me doing it now is not going to help you, okay? Okay, so those are our first friction factors, and so now we can check closure. So 100 meters. So, well, why don't I do this? So I need delta H1, I said. So F1 L1 over D1 plus KE V1 squared over 2G. Lots of stuff. So 0.017 times 1000 over 0.25 plus 0.5, all that times 4.07 squared over 2 times 9.81, and that is 57.4 meters. Okay, so that is the first delta H term, this one up here, and then I need to do the second one. Again, it would just be a lot to write that. To write this whole equation would be a monster in one line, so I'm splitting it up a little bit. F2 L2 over D2 plus, I need a 1 there, and then a KC and KV times V2 squared over 2G, and so that is 0.019 times 2000 over 0.2 plus a 1 plus 0.0, did I say it was 0.02? It's so small, it doesn't really matter. Spend all that time to look it up, and then it doesn't matter. 6.37 quantity squared over 2 times 9.81, and that came out to be 405 meters. So the head losses in the first one are 57.4, and the second one they're going to be a lot more because it's the same flow through a smaller pipe, so it's going to, you're going to have to push harder because the velocity is bigger. So a lot more energy loss. So now we can check closure. I shouldn't have written that really yet. So check closure. so we have delta Z equals delta H1 plus delta H2, and so that's 100 meters equals 57.4 plus 405 meters. So this is clearly not true. It did not close. Our guess for Q, when we followed the whole logic through, did not come out to be true. The question is, what should we guess next for Q? So need to continue. And so what we found is that the head losses were bigger than the head that was available. So that means that Q is too big or too small. Which one would it have to be? Stop and think about that for a sec. It's got to be too big, because if I decrease the head, or sorry, if I decrease the flow rate, then I will decrease the head loss. The more I try to push through there, the more head loss there's going to be. So what this is saying is that this 100 meters is simply not enough head to support this big flow rate. So the actual flow rate is going to have to be something less than that. So flow is too big because delta H required is bigger than delta H available, if you will. Okay, so the required head for this is 460 something, and then what I have is 100. So that means that I've got to bring Q down. So let's try Q is equal to let's try Q is equal to 0.1 meters cubed per second. If I do that, I'm not going to write all the details down. I'm simply going to give you what the values were that I got. V1 is 2.04. V2 is 3.18. Reynolds 1 and Reynolds 2. 5 times 10 to the 5th and 7 times 10 to the 5th. F1 and F2 I got were 0.018 and 0.019. And then the delta H for each of those, 15.3, and delta H2 is 101.3. So this is still bigger than, so still too big, but close. Okay, so I'm going to need to pick another one, and so if I do that Q is equal to 0.09 cubic meters per second, this is going to get me close. And so if I wanted to do this really accurately, I would need to, I could do it in Excel. And so I guess we'll leave parallel pipes to the next video, because it looks like this was over an hour once we put these two together. So hopefully these videos help you understand pipe problems a little bit better, and they can get you thinking about pipes in series. So we will pick up there in the next set of videos for Thursday.